Hello, everyone. Great to be here. I'm a CTO of Deep Instinct, so all the numbers that you're going to see there about the market cap and the money are not really interesting to me, but I can summarize my entire interest in what we are doing in this single number. There are 1 million new malware created on a daily basis. And even some of those that are not really sophisticated, like WannaCry, they cause something like this. This is from the quarterly earnings report of Maersk, the largest shipping company in the world. In the last week of the quarter, we were hit by a cyber attack, which mainly impacted Maersk Line, APM terminals, and Damco. Business volumes were negatively affected for a couple of weeks in July, and as a consequence, our Q3 results will be impacted. We expect the cyber attack will impact results negatively by $200 to $300 million, just due to the WannaCry ransomware. And similarly, at that time, FedEx, Maersk, the large pharmaceutical company, reported similar losses. So the best way for me to convey the complexity of detecting new malware in cybersecurity is not to talk about cybersecurity. So let's ignore cybersecurity for now and focus on my dog, Tyrion. Not Lannister, but Tyrion the Cavalier. And that is how he welcomes me every morning. I'm on the bed, he comes and says good morning, and I easily recognize him, even after a sleepless night. However, sometimes when he's cold, I find him in situations like this, or even cuddling with his toys, something like this. But I easily recognize him, even in this situation. So imagine a world in which I show you a picture, and you easily recognize the dog. Now I modify just a few pixels, and suddenly you don't recognize anything. You don't recognize the image. Sounds ridiculous, right? This is the world of cybersecurity. Of those 1 million new malware every day, vast majority of them are very slightly mutated. And even nation-state attacks, they're at best 10 to 20% different. So the problem is much more challenging. So how do today's best solutions deal with it? Most of today's good solutions, not just the antivirus signature-based ones, use traditional machine learning. In traditional machine learning, still the problem is that they're relying on heuristics and features, and by the time they detect something, the developers of the malware usually can easily mutate the file and create a new version, which takes a few more weeks or months until it's getting detected. So let's look at traditional machine learning versus deep learning to see what are the differences. In traditional machine learning, we cannot feed our raw data directly into the classifying module. For example, if you're using traditional machine learning for computer vision, for dog detection, you cannot feed raw pixels directly into your machine learning module. Instead, you first need to do feature extraction, a process through which human experts tell us what are the most important features, the properties present in the data. So if the problem is, let's say, face recognition, the most important features would be distance between pupils, distance between nose and a mouth, proportions of the face, texture, color, etc. If it's an executable file, we can imagine the most important features to be, let's say, the important API calls, registry keys, etc. So we first do feature extraction, and then when we convert the raw data into a few tens, hundreds, or thousands of features, we feed them into the traditional machine learning module. The feature extraction part is quite problematic, not just for cybersecurity, wherever we apply it in machine learning, for two main reasons. First, by converting the raw data, millions of pixels, or in our case, millions of bytes, into a small list of features, as good as they may be, we are still throwing away most of the data that we have. But secondly, and more importantly, even the best human experts can think in linear terms. We can think of linear patterns. We cannot really grasp the rich nonlinearities in the data. To give you a more intuitive example, the easiest task for our brains is detecting cats and dogs. If I show you a picture of a cat or a dog, in a few milliseconds you will detect it with 100% accuracy. But can anyone explain what is the difference between a cat and a dog? Now, I won't torture you here. That's what I do to my students at university. But for many minutes, we can go on this game, and most people will not come up with even a single good feature that discriminates between cats and dogs. People will say, well, a dog is bigger, but wait, there are smaller dogs. A dog's muzzle is longer, but wait, there are flat-faced dogs. At some point, somebody would say, oh, the pupils. The pupils of dogs are more circular, while those of the cat are more elliptic. And at that point, I showed them this picture. A cat and a dog sleeping beside each other with their eyes shut, and then all of you, in a few milliseconds, recognize what's a cat and what's a dog. So we, having a real neural network, are very good at predicting what we see, but we're very bad at feature extraction. If we're having trouble coming up with a few good features for the easiest task for our brain, we can forget about the most complex task for our brains, like an executable file or a PDF file looking at the raw values. Deep learning, on the other hand, deep neural networks, is the first and currently still the only family of methods within machine learning that can skip feature extraction. The way we apply end-to-end deep learning is always feeding the raw data directly into our deep neural network. So when we apply deep learning for computer vision, the input is raw pixels. No image processing, no pre-processing. For speech recognition, amplitudes and frequencies. For text understanding now, more and more results are obtained using just characters, not even words. And similarly, we would like to apply deep learning directly on the raw data. So that was the idea that we started working on. So when thinking of applying deep learning to cybersecurity, we quickly find out that the problem is much more challenging than applying it to, let's say, computer vision. If we take an executable file and we would like to treat it as if it were an image, this is how the image looks like. Something like this. Looks like just random things, random noise. This is not random. It's full of correlations. The correlations are simply not local. In neural networks, when, for example, we're using convolutional neural networks, the most popular flavor of neural networks, we're relying on local correlations. If a certain pixel is blue, most probably adjacent pixels are also blue. We're using those kind of local correlations. Here, we don't have this kind of local correlations. In computer vision, when we have images, inputs of different sizes, we can just resize the image to a predetermined fixed size. In our case, we may have a file which is 100 kilobyte, 100 megabyte, or 100 gigabyte. We cannot just resize an executable file to a predetermined fixed size. So we see that the problem is much more difficult. The input varies in size, in format, lack of local correlations. So what we had to do is spend nearly a year modifying neural network methods to be able to detect non-local correlation. The input layer be of dynamic size, to be able to absorb dynamic input sizes. And the moment we make these kind of modifications, let alone the inefficiencies of publicly available deep learning frameworks like TensorFlow, PyTorch, etc., which are frameworks developed by researchers for researchers. They're extremely inefficient for real-world productization. But even had we wanted to use them, it would have been impossible. All these publicly available frameworks expose high-level building blocks. In this case, we entirely changed the backbone of conventional neural networks, to the extent that when we wanted to implement it on NVIDIA's CUDA, we even couldn't use cuDNN, which is the high-level building block of NVIDIA for deep neural network. So we had to implement it directly on CUDA. After we've done that, we obtained about 100 times speed up for training compared to CPU. As you know, GPUs, because of their inherent parallelism, are much better suited for processing neural networks than CPUs. So let's see how we use this deep learning framework that we've developed that is good for finding non-local correlations, varying input sizes and different formats in action. But before that, let's see what we are not using. Since we're focusing on end-to-end deep learning, from raw byte values to outputs, we do not need signatures. You need signatures that are very good for memorizing existing malware. But even if a malware is slightly mutated, then signatures are useless. We care about detecting new malware, so we don't need that. We don't need to do sandboxing. Sandboxing is a very useful tool. You take a suspicious file, you run it in a virtual environment, sometimes up to several minutes, to gain more information about its dynamic behavior. In our case, all our prediction is based on static detection and prevention. We view each and every computer file as if it is an image, with the only difference that instead of a bunch of pixels, it contains a bunch of bytes. So executable file, PDF, Office, Android APK, they're all a bunch of bytes. We can just feed them into the neural net. Additionally, we don't use traditional machine learning, due to which we don't need to do feature engineering. We don't need to try to be smart and understand what are the important features. We just feed raw values. We don't need real-time connectivity because, as we will see, we're doing the prediction part of the neural net on the devices that we protect. We don't care about any manual classification. Because we don't do any dynamic analysis, we won't need to wait for execution of the attack. If you're using dynamic analysis and sandboxing, if you download the file, I cannot tell you, well, wait for a few minutes until we decide if you can run it or not. You will run it, it will infect half your network, and then we will say, oh, remember that file 5 minutes ago? That was malicious, good luck with that. That's only detection. In our case, we're doing detection and prevention. And finally, by training a neural network, we don't need to do any frequent updates. If you're using signatures, you need to update them frequently. Using neural networks, hopefully, it understands the overall patterns. So when there are new malware, it doesn't need to undergo frequent updates. We update once every 3 to 4 months the neural net. So if we don't do any of this, let's see what it is that we actually do. So the training phase of what we do takes place entirely in our laboratory. No training on customers' premises. We have a large, continuously growing data set of now close to 1 billion samples, containing several hundred million malicious files and several hundred million legitimate files. Different file formats, different operating systems. So during the training time, we feed all these files into our deep learning framework, running our GPUs in our laboratory. The entire training cycle takes slightly over 24 hours. But when we have finished the training, now we can use it in inference. We have optimized our training part for NVIDIA's GPUs, because today that's the best device for training. However, even though today nearly all prediction and inference is also done on GPUs, we found out that if we especially optimize the prediction part, that the neural net just needs to see a new sample and provide a prediction, it can be very efficiently run on average CPUs as well. So in prediction part, we can just feed any file. Our neural network is running on the pre-trained neural net and running on any device, or laptop, desktop, server. And for each new file, in a few milliseconds, it can provide a prediction for whether it thinks it's malicious or benign. So the actual real-world deployment looks like this. We have on any device that would like to protect an agent, so any laptop, desktop, server, mobile, we put a small lightweight agent. The agent is small and lightweight because it doesn't care at all about anything. It just looks at the file system to see if there is any new or modified file. Together with this agent, we put a copy of that pre-trained neural net that we trained in the laboratory, a few tens of megabytes in total. So the brain and the agent, they reside physically on each and every device that we protect. So during the actual runtime, the moment there is a new file on the file system, the agent blocks it, allows the brain to provide a prediction, which takes a few milliseconds. And if it's deemed malicious, it removes it pre-execution. And if it's deemed legitimate, it just unblocks it and it proceeds. The whole cycle from the moment the file is observed to the moment it's removed takes a few milliseconds. Entire memory usage, a few tens of megabytes. Just the waits for the neural net, nothing more. And the average CPU usage, practically 0%. Most of the time it's idle, and when finally something happens in a few milliseconds, it's over. So if we summarize the comparative advantages that using end-to-end deep learning provides us, they would be the following. Because neural networks, by the way, similar to our brain, they are very slow for training, but very fast for prediction. It takes you years to learn a new language, but when you learn it, you will use it instantaneously. Your inference is very fast, similar to artificial neural networks. We can provide real-time detection and prevention. Unlike most other solutions which do the dynamic analysis and only detection, we can do pre-execution prevention because it takes a few milliseconds. While we're very good in detecting currently existing threats, you don't need deep learning for that. You have very good antiviruses for predicting currently existing malware. Our deep learning-based approach is especially good for detecting new malware, mutated files, nation-state attacks. We will see shortly. If we're using traditional machine learning, we need to do feature extraction for each file format, which means that we can spend a year understanding the features of an executable file, and then when we want to move to PDF file, back to square one, understanding PDF files, doing feature extraction for them. In our case, because we don't care at all about any file format and any feature, we can run on any file format, actually any operating system. Our solution, the same brain works on Windows or Android. Not because we have spent time understanding the files and operating systems, but because we completely don't care about that. Any kind of file is just a bunch of bytes. Because the resulting brain is so small and the inference on the CPU works so fast, we can put the brain on the device itself. Whereas most other solutions rely on the cloud, so there is an agent, when they see a file, they upload it to a server or the cloud. In our case, we don't do that. So if your laptop is for months disconnected, or your mobile device is in airplane mode, all the detection and prevention will take place as usual. We don't need to have any continuous connection. And finally, any one of us that have managed large-scale projects, you know the sleepless nights when we go to POCs and we get the report that there was a blue screen on deployment and we have many kind of problems. Thankfully, in our case, we have fast and easy deployment again because all this sophistication is hidden in the laboratory. When you do the deployment, what's there? A small agent, a stupid agent that just looks at the file system, and a neural network that frankly is doing just a few million operations of multiplication and addition. So there are no blue screens, very seamless implementation. All the complexity is hidden in the laboratory. So looking at comparative results, during the past year, we've already been deployed in many large enterprises, Fortune 500 enterprises in North America, Europe. On average, when tested on new malware by customers, we obtain about 99.7% detection rates of new files. And in independent tests, we stand at around 99.3% detection of new files, with a false positive rate of under 0.1%. But these numbers in itself, these numbers are completely meaningless. In some POCs, we get 99.9% detection. In some others, we get 95 or even lower detection. This doesn't sound like a good message to say to the customer, but what I always say that we don't guarantee any detection rate. However, on any data set, no matter how challenging it is, deep learning will have a relatively higher detection rate in comparison to traditional machine learning. And similar to the results we see in computer vision, speech recognition, text understanding, computer games, that when deep learning is applied, it is obtaining relatively higher accuracy than other methods. This is what we're seeing here. So sometimes we get 99.7, the others get 98, 97, and sometimes we get 90%, and machine learning-based solutions get under 60% detection. A more interesting approach is to look at what happens for the results if we look at the timeline. So let's imagine that this axis is the detection rate, and this is time. So imagine today we take the latest version of Deep Instinct and the latest versions of traditional machine learning-based solutions. And let's download the newest malware that appeared for the first time tomorrow. Thankfully, we have a huge amount of new data every day. If we compare them to each other, Deep Instinct will have a higher detection rate because of the advantage of deep learning over traditional machine learning. Interestingly, what happens when we freeze these solutions and don't update them? So every day that passes, the malware in the wild, they evolve. They gradually but continuously evolve. So as we don't update all the solutions, their detection rate should drop. It drops like this. So for traditional machine learning-based solutions, if you don't update them for a few months, the detection rate literally falls off a cliff. But for deep learning, even when not updated for 6 months, the detection rate goes down very, very slowly. And these are the kind of results that assist us in having much higher detection rate in comparison to other traditional machine learning-based solutions. So since a year ago, we were doing many deployments, and the POCs were showing to the customers that we have much higher detection rates. But the criticism that we've always faced, and every one of you that has done a black box algorithm like neural networks have faced that, is, okay, great, you detect much more than others. But when I see a detection, well, I trust it, but why is it malicious? So initially, our reaction was, why do you need to know? Trust us, it's malicious. At some point, we saw that this line of explanation is not going very smoothly, and we cannot really understand how neural networks reach the conclusions they reach. So we thought about training another neural network for detecting malware families. In this case, because the primary prevention is done by the static module that is running on with the agent on the end devices of the customers. When a file is detected and prevented, then a copy of that is sent to our server within the premise of the customer. Now we have all the time in the world. It has already been prevented. Now we can do whatever we want to do just for forensics and gathering additional information. We can do a dynamic analysis, run it in a sandbox, but in this case we're not running it in a sandbox to decide if it's malicious or not. We've already decided it is malicious. We want to understand what kind of malware it is. So if we run it in a sandbox, this is the kind of output we get. This is the output of all the APIs it calls, the parameters it sends, and there are many kind of methods that try to extract features here to tell us what are the important features and then do traditional machine learning. But let's continue with our agnostic approach. Assume this is just a bunch of raw data. Assume this is a text written by Shakespeare. We don't need to understand anything about cyber, and we don't want to do any feature extraction. So we just scanned the data set that we had to find what are the most frequently appearing 50,000 words. Why did we do that? Because there are millions of words that appear, like the addresses, the junk that appears. So we took 50,000 most popular, most frequently appearing words. We converted each file, each dynamic analysis file, into a binary vector, Boolean input vector of size 50,000. For each of those words in our dictionary, whether they appear or not. Basically, we're looking at that dynamic analysis file as if it's text. We're not using any cyber knowledge. We feed that into a 10-layer deep neural network. The output layer of the neural network has 7 different categories. Basically, what we want to do is give an input for the deep learning model to tell us whether it's a ransomware, whether it's a backdoor, it's a dropper, a spyware, a virus, worm, or potentially unwanted application, like an adware. The results surprised us. It's working amazingly well, more than 99% accuracy. Of course, we took a data set with ground truth, we trained on some, tested on the other. The results were so good that immediately after this worked in the laboratory, we just took it and put it in product, and since then it's working there. So this is a screenshot from our actual product. You go into an event number 8227, and we have deep classification. 97% it's ransomware, 3% it's dropper. How did we come up with those values? They're just the confidence values of the output layer of the neural network. We just take those values, put them here, and our customers are very happy with that. We give them the illusion that we know what's happening in the black box. But what if we try to take it a step further, this kind of attribution? Everyone's talking about cyber warfare today. Every nation state is allegedly working on creating better and better malware, and they're blaming each other. Can we use similar approaches, but instead of trying to classify which family of malware it is, do attribution? Who wrote this malware? Again, those of you who are doing text analysis will feel at home here. We're doing text attribution. Instead of trying to detect whether this is written by Shakespeare or by Charles Dickens, we're trying to do whether it's written by Russia or by US, let's say. What are the challenges here? The challenges are that these are, first of all, the most sophisticated types of malware. They use the most advanced evasive methods. We have small training data sets. We cannot use, we don't have millions of samples, unfortunately, or fortunately. And finally, there is intentional attribution manipulation. We have seen, for example, malware that after manual analysis, with high confidence, we can say they're developed by China, but they include Cyrillic text, Russian text, so that it is attributed to Russia. And many different countries trying to blame each other so that a shallow analysis would point to the other. So we obtained a data set. Our data set was published by Kaspersky. They have done the most extensive labeling. They've manually analyzed, said, well, this is written by Russia, this is by China. We gathered these families of malware, a total of 1,600 files attributed to either Russia or China. The most, these two countries apparently, allegedly write the most number of malware, so thanks to them, we have the most number of training samples. We encourage other countries to contribute more training samples to us. So we have 500 files from each class, for each one of them, for training. And one important thing is for training and test, we separated not only the files naturally, but also file families and on a temporal axis. So if these two files are attributed to the same family, we make sure that we don't have a situation when one is in the training and one in the test set. Entire family is either in train or either in test. This is the most realistic approach. The results showed 94.6% accuracy. So given a new malware, very high confidence in attribution, whether it was written by Russia or China. We're now working on extending it to additional attributions as well. And if you're more interested in reading more about this, we published our entire approach in 2 papers. One of them appeared in International Conference Artificial Neural Networks last year, and the extended version of that just last week appeared in the journal Entropy. We go into all the details of how we use end-to-end deep learning for performing malware classification. So to summarize, using end-to-end deep learning without any cyber-related knowledge, just by looking at the raw data as if they're a bunch of bytes, we managed to do malware detection and prevention. We're doing malware classification, and now we're also doing malware attribution. During the past year, in nearly every POC we participated, our detection rates were much higher than traditional machine learning-based solutions. And to the extent the past year we received nearly every important award in cybersecurity, and also beyond that, NVIDIA selected us as the most disruptive AI startup of 2017, World Economic Forum as a technology pioneer of 2017. But my conclusion would be much simpler than all this. End-to-end deep neural network works. Even in the areas which are much more challenging than computer vision, even in the areas that you cannot use TensorFlow and publicly available frameworks, even in the areas that you have to spend an entire year trying to make it work, when you manage to implement end-to-end deep learning, usually the results are a huge improvement over all previous methods. Thank you very much. And by the way, those of you who are more interested in reading about what we discussed here and many other things, recently I published this book, Deep Learning for Dummies, published by Wiley's. Most of the book is not about cybersecurity, but we also cover it there. And you can download the free version of this book at our website, deepinstinct.com. Thank you very much. I'll be happy to take any questions. So the question was, how do we deal with adversarial attacks? Or even generative adversarial networks, deep neural networks that are designed for fooling an existing neural network. First of all, it is possible for them to attack us. And one of our active areas of research currently is internally using generative adversarial networks and other kind of adversarial methods to try to fool our method, such that we improve the training. We fool ourselves and not others fool us. However, using deep learning for cybersecurity for adversarial manipulation is much more complex than in other areas. For example, assume you would like to fool an object recognition module to think something is a cat when it is not a cat, using generative adversarial networks. You start by randomly manipulating some pixels, seeing the results. If you take an image and you randomly modify a few pixels, the result is a valid, legitimate image. In our case, if you take an executable file and you modify a few random bytes, most probably you've broken the file. It will no longer work. You may manage to fool us, but it will no longer work. It is not to say that these methods cannot be applied here, but that their application is much more complex. We take additional measures also. For example, when we feed those hundreds of millions of files into our deep learning module during training time, we never feed them as it is. We have an automatic mutator. Each time we feed them, we modify them by up to 20–30%, and then do the training on them. In each epoch, they undergo mutation. And in our mutations, we don't care if we break them, because it's static. It just tries to learn various modifications of that. So this is a very interesting area of research, and we expect in the next few years we will see some interesting attacks using adversarial methods. Okay. The question is that if we're not using convolutional neural nets, not fully connected neural nets, then what are we using? Convolutional neural nets and the greater family of neural nets that are locally connected, their problem naturally is that they're utilizing local correlations which are not present in our case. We wish we could use fully connected networks, but you can imagine with big inputs, it will take us hundreds of years to be able to train something useful. So this is the main modification that we have made to take fully connected networks. And by the way, you can take fully connected networks and turn them into locally connected, not necessarily convolutional, but they will not be useful. In our case, we modify them such that they would be able to automatically find non-local correlations. That connected, especially in the input layer, that is dynamic, and it can take different input sizes. So after we make these kind of modifications, it's impossible to implement them on any publicly available framework. So we had to go through the ordeal of implementing everything from scratch. Thank you very much.